We saw border gateway protocol by design itself. It is designed to meet all the border policy in path selection. It is very flexible than any other protocol to apply the policy based path selection, policy based routing. No other protocol is that well built. So that's one reason. Secondly, the this protocol, though it is designed to be in the borders, even the name says it is border gateway protocol, but it is also enabled within the autonomous system. That is a big reason. See, we have IGP protocol to run within an autonomous system. But there is also another very important, valid reason why we also should enable BGP within autonomous system. We are going to discuss about the reason. But what I'm coming to say is, even though border gateway protocol is meant to be in the borders, we have a very good reason to enable it inside an autonomous system. That doesn't mean we are going to replace IGP protocols. We still need OSPF, EIG, RPA, RIP. On top of it, we are also going to enable BGP. So IGP and BGP is going to coexist. Now, when I enable BGP between the different autonomous system routers, a name is given called eBGP. When I enable between the routers that are within an autonomous system, different name, it's IBGP. Why should be two different names for a single protocol? Because we have different policy within an autonomous system, and between autonomous system we have different policy. So the behavior of BGP also should be different, and it is different. That's why the name is different. BGP in service provider, unless you write policies, packet won't even go out. Even a single update won't be sent. Not even a single update will be sent if you don't write a policy, RPL, route policy language, but not in the routers that we have in enterprises. I'm talking about ASR devices. Just to explain you now, in IBGP, you don't need to write a policy for updates to be sent and received. Whereas in eBGP only, you need to allow pass the updates to go and updates to come in. Why? Between the borders, we are strict. Within the autonomous system, we are not strict because it's our own autonomous system. So the protocol is one. They're not behaving the same way. They have different relationship, a strict relationship with eBGP neighbor and a liberal relationship with IBGP neighbor. That's why name also should be different. So that When I say IBGP neighbor, you will understand, okay, liberal. When I say EBGP neighbor, then you will understand, okay, it's a strict relationship. By the name, we'll understand what sort of neighborship they will have. See here, what are called as peers or neighbors? We know BGP uses TCP. If two routers can establish the three-way handshake successfully with the port number 179, they can now form neighbor. After which the updates are going to be shared between them. They are called as BGP peers or BGP neighbors. When two routers can establish TCP connection using port number 179 and then followed by BGP negotiations successfully done, updates shared, they are called as BGP peers. First is TCP because it's a TCP based protocol. Only after TCP synchronization, three-way handshake, only after three-way handshake, all other things will follow, like BGP open message, and then BGP's notification, BGP updates, which we saw in the previous chapter. So peers are nothing but neighbors. It's not simple neighbor, it's a TCP neighbor. Now, EBGP is external border gateway protocol. When we run BGP between the routers that belong to different autonomous system, in our example here, router D and router Y, they don't partake in same autonomous system. You see, D is in 65500, Y is in 65000. Between D and Y, the association is an EBGP association. Between D and Y is EBGP. Likewise, C and X is EBGP because they don't belong to a single autonomous system. Now, for EBGP, there is a basic default constraint. What it is? EBGP neighbors need to be directly connected. EBGP neighbors by default need to be directly connected. Yeah, that's the constraint. That's the basic constraint. EBGP neighbors by default need to be directly connected. See, again, the word default is what I want to underline. By default it is, which means it can be overridden. By default, need to be directly connected in order to form EBGP neighbor. If there is a need for you to form neighbor with the links that are not connected directly, it is possible by doing some additional tunings, not by default. By doing basic BGP configuration, don't expect neighbor between the links that are not connected directly. So there is some additional configuration needed in order to form a neighbor between the routers which negotiates with links that are not directly connected. Meaning, if I want to form neighbor with the loopback interface address of D and Y, it is not possible by default. You need to use the physical interface address of this interface and this interface. Only then the neighbor comes up. That's what the meaning here. If you want to form neighbor between D address and Y address, which is the loopback interface, not allowed by default because they are not directly connected. But by doing some additional configurations, you can achieve it if it is necessary. Internal Border Gateway Protocol IBGPs are the neighbor that are within the autonomous system, that are within the same autonomous system, and the neighbors do not have to be directly connected. What I mean is, what does this line means? It means that A and C can form neighbor, we not having BGP here. Not necessary. See, if it is OSPF, you have to enable OSPF on A, B, and C. You cannot form neighbor between A and C without B in IGP protocols. In BGP, it is possible. A can form neighbor directly with C, even if you don't have BGP here. How is that possible? BGP uses TCP, no? Take for example Telnet. If I want to telnet from A to C, is that possible? Of course it is possible. To telnet to C, there is no need for you to telnet to B and then from B to C. Not necessary, no? Telnet uses TCP. BGP also uses TCP. So you can directly from A to C establish neighbor. But for telnetting, what is needed for you to telnet from A to C? What is needed? Reachability. A should reach C. If you have reachability, if you can ping from A to C, definitely you can also telnet from A to C. Likewise, when we already run IGP protocols like OSPF, when we already have some IGP protocols like OSPF in our autonomous system, A can ping C. There is reachability between A and C. There is reachability. With the help of that reachability, BGP's negotiation is possible and the neighborship comes up between A and C. IBGP neighbors do not have to be directly connected. But this is not applicable for eBGP by default. I'm saying again by default. If you want to form neighbor between Y and A, it is possible even in eBGP, but you need to do some extra tunings. Whereas in IBGP, you don't need an extra tuning because they do not have to be directly connected. In eBGP, you need extra tunings. The reason is it is eBGP. because it is between different autonomous system. Your security is more priority than forming neighbor. That is why by default they have designed not to form neighbor with remote routers or between the loopback interfaces of the neighbor. It needs to be directly connected. eBGP neighbors need to be directly connected. Whereas IBGP is within your autonomous system, you don't have fear because it's your own autonomous system. Because it's your own autonomous system, you don't fear. So you allow neighbor between A and C, which are remote routers. They're not same directly connected. They are remote. As long as the reachability is there between A and C, the neighborship is going to be there. Next, IBGP in a transit AS. IBGP in a transit AS. Let us discuss about how your ISP should facilitate the routes from A to F. See, the middle one is an ISP. It's a service provider. It's an ISP. It's a transit. All ISPs are transits. Correct, no? The customer is connected to one ISP and he communicates to some customers in some other ISP somewhere remote. So all the middle ISPs are transits. They are neither source nor destination. They are simply transit. They need to forward the packet. That's why we pay the service providers. That's the job of service provider, to transit our packets faster, guarantee delivery, secure, a lot of tunnels available. That is what a service provider provides, a transit for our traffics. Now, you see there's a customer called A and F. A wants to ping F and vice versa. So the routes of F and A, the route updates of F and A is shared and distributed by the ISP. For example, in F there is a network called F dot F dot F dot F connected to loopback. In A there is a network called A dot A dot A dot A connected to this loopback. If A wants to ping F dot F dot F dot F, and if F needs to respond back to A, what is needed? A needs the route to reach F. A needs the route to reach F in the routing table. And F needs the route to reply back to A, because the traffic is coming from A now. From A you are pinging, so your source address is A. If F needs to respond back, it needs to know the route to reach A in its table. For these routers to know the route networks of remote, the middle autonomous system should forward it. When F advertises F dot F dot F dot F, it should come and reach the routing table of A. Likewise, in A is advertised, the ISP should distribute it to F so that it will be seen in the routing table of F. Only then the communication between these two is possible. So the route updates, not just transferring, allowing your packets. See, for your packets, first of all, your ping packets, your telnet packets to go. Before your ping packet and telnet packet go, what is needed? The route update should be transited. The route update should be shared, distributed across. Route updates. Yeah. The route advertised from F should be given to A, and route advertised by A should be given to F. The distribution is needed. The middle autonomous system, ISP autonomous system, needs to facilitate this. Let's see how middle autonomous system can provide the service. One way, what some people do is they take routes from BGP and distribute it to OSPF. We call it as redistribution. Now what will happen? The AAA advertisement is now carried as OSPF updates to E. And now on router E, they redistribute OSPF back to BGP. In that way, that AAA is now carried by BGP to F. And now AAA is learned. This happens on the other direction also. When FFF is advertised from F via BGP, router E will redistribute from BGP to OSPF. Why? Because I don't have BGP on these routers. We have BGP only on the border routers. Because you don't have BGP, we have to carry using OSPF. OSPF carries to the other side. But you know, this is a wrong approach. This is a solution, but it's not the best solution. This will work, no doubt, but not the best solution. I'll give you 3 reasons why this is not a best solution. Number 1, we are having BGP here between A and B and E and F for a very important reason called policy. We have some policy to reach the customer A and F. That is why you go for BGP. If you don't have policy, you would have enabled OSPF there. The reason for we having BGP is we have policy. Now, when I redistribute from BGP to OSPF, what will happen to those policies? Gone. When we redistribute from BGP to OSPF, all the attributes that are coming with BGP is gone. OSPF cannot translate all those attributes. OSPF don't understand any attributes. OSPF knows only one thing, what? Cost. Correct. So the purpose has gone now. The purpose of we enabling BGP is to have attributes in path selection. But when we take BGP and redistribute to OSPF, OSPF knows nothing about attribute. It goes as OSPF update without any attributes to the other side. And other side from OSPF you are giving to BGP. What is the use? You lost all the attributes. The attributes that were set by A is gone when it is received on E. Likewise, the attribute that is set on F is removed when you redistribute from OSPF to BGP. Attributes gets removed. Then there is no point of V running BGP between A and B and E and F. That's one reason. Secondly, when we redistribute, the process utilization is going to be very huge. Translating from such a big protocol like BGP into small protocol like OSPF and back from OSPF to BGP, this is not a simple thing. It's going to take a lot of processor. It is like you are trying to accommodate passengers coming from a jumbo flight, like 300 passengers, into a small minivan. You need to do a lot of sacrifice there inside a minivan to accommodate 300 passengers who landed in Istanbul because of emergency from Frankfurt to Delhi. A passenger flight which supposed to come to India in 9 hours took 3 days to come because they landed in wrong airport day before yesterday for emergency. One passenger was in emergency. While they were flying, the nearest airport was Istanbul. They landed there. And immigration process and all not that easy when you do emergency landing. You don't have any visa for all those 300 passengers to enter into Istanbul. If it is airport hotel, no problem. But airport hotels don't have that many accommodations. You need to stay outside or you need to stay inside the airport till the flight takes off. See, it's not that easy to transport everyone from the plane to the airport hotel. Hotel cannot accommodate 300 people. And passengers will not adjust in one bed, two passengers. Why should they accommodate someone? No one will be willing to do that. It's not a school hostel, dormitory. Likewise, trying to accommodate BGP into OSPF is that difficult. But we do that by simply putting redistribution command. That is going to take a lot of processor on both router B and E. Thirdly, why we should not do this redistribution. When I take BGP route and give it to OSPF, OSPF is not only running for BGP, it is also running for internal networks. So now there is a danger of external networks getting mixed with the internal networks. What if the same FFF is also there inside the provider's network? What if that same network? It will conflict. Not only that, when you redistribute from OSPF to BGP, not simply AAA is getting redistributed, even the internal networks gets redistributed. Then there is no security. You no need then two protocols, you can simply run OSPF from end to end, A to F. Because your inside network and external network get mixed when you do redistribution. Now, to avoid, you need to do a lot of filtration here. You need to filter all those internal routes going to the customer, which is unnecessary task, difficult task. So what is needed? You need to run BGP on every router. See, I told you in the beginning, we have a good reason why we should run BGP on every router inside an autonomous system. This is the reason. If you don't run BGP on all routers, then you will do what? Redistribution from BGP to the inside routers, routing protocol. But it's not recommended. A lot of drawbacks which we discussed. We discussed 3 drawbacks. Number 1, process utilization when you do redistribution from big protocol to small OSPF and small OSPF to big BGP. Secondly, we saw the external network and inside network get mixed. And to avoid inside network going to the customers, we need to put a lot of filtration, which is unnecessary task and difficult task. And thirdly, we lose all the attributes that were set in BGP if you are redistributing from BGP to OSPF. Okay, so redistribution is not a solution. You need to run BGP on D as well as C. We need to run BGP on D as well as C. Now you may say, like, why should we run BGP? When BGP can form an IBGP between B and E. When B and E can form IBGP, why do we need to run BGP on D and C? Remember, we learned earlier, IBGP need not be directly connected. We saw here. See the second last line. The neighbor do not have to be directly connected. Yeah, it's true. B and E can form neighbor directly. Then you may think that then there is no need for BGP on D and C. Actually, to form neighbor, there is no need for BGP on D and C. But for the packets to be forwarded, see 1.1.1.1 coming here, 1.1.1.1 using BGP. Now 1.1.1.1 is also available here. It is also available here. Likewise, here let's say you have 7.7.7.7. It is available now everywhere, wherever BGP runs. In the routing table, you learned. No doubt, you will learn it. Even though D and C don't have BGP, you will learn the BGP updates. Between B and E, there will be route update sharing, and A and F will learn these routes. No doubt, they learn these routes. But when you try pinging, see this network, when you try pinging, packet will go up to here, but C and D don't have any information about 10 network. Why? Because there is no BGP running. Who is advertising this network? Is it OSPF? No, BGP. BGP only provides 10.000 to B, and B provides it directly to E, and E is provided to F. There is no chance of D and C knowing about 10.000. Even though the update packet was passing through D and C. D and C has got no rights to open it because they don't run BGP. It is not destined to them. It is not delivered to them. It was given to D to forward it to E, so D will simply forward the updates. It won't get synchronized with the root updates because there is no BGP. So what happens is there will be a packet drop. There will be a drop on C and D. So what is the solution? Solution is you need to run BGP on every router so that this 10.0.0.0 network will go here. Via BGP, it will also be learned here because there is BGP running here also. And it will be learned here, everyone knows about 10 network. So someone can ping from F to A. Now there's a very big difference between the above picture and the below picture. And this page is very, very important in this chapter. This page is important. See the last line that is written here. By default, route learned via IBGP are never propagated to other IBGP peers. So, they need to be full mesh. What does it mean? It means running BGP on all router is not enough. Also need to be forming peering between every single router. Simply running BGP is not enough. B should form neighbor with D also to E, which is not seen here. That's why it is partial mesh. Whereas if you see here, B is forming neighbor with D as well as E, which is what full mesh means, meaning everyone should have neighbor with all other. Even if they are not directly connected, all should have neighbor with all of them. So why it is needed? Why full mesh is needed? Because to prevent loop, there is a rule. Route learned via IBGP or never propagated to other IBGP peer. Meaning, even though we are running BGP here and here, the route coming from here, the updates coming from B to D, D will not give it to E. It will not. See, a route learned via IBGP. D is an IBGP to B. Route learned via IBGP are never propagated to other IBGP. D learning route from B is an IBGP learning. Route learned via IBGP are never propagated to other IBGP. If you want that propagation to happen, you need BGP to directly give it to E like it gives to D. That's why you need to have full mesh. Now, why is this rule first place? This rule is always enabled by default. You can override it by setting something called route reflector. But why is this rule? Let us assume these four routers are connected like this instead of that way. If the four routers are connected like this via a single common layer 2 switch, assume, but it is not like this. This is having separate broadcast domain, separate LAN. You see four different LAN. But what if you have one common LAN, one common broadcast domain? In this scenario, this rule is important. This is what you will see mostly in the production. That's why this rule is enabled by default. So for example, a network is coming to this router 1.1.1.1, and this rule says if R2 learns, if R2, R3, R4 learns the network from R1, if R2, R3, R4 learns the network from R1, if they learn the network from R1, that 1111, they should not propagate it to other IBGP neighbors. That's good, no? See, R1 has given the routes to R2, R4, and R3. Why R2 needs to propagate it again to R3 and R4 and R1? There is no need. Already R3 knows about 1111. R4 knows about 1111. There is no need to propagate again. That's why it is never propagated. Route learned from one IBGP should not be given to other IBGP. That is good, because if you give, it becomes duplicate. It will definitely become duplicate, and it will cause loop. To avoid that, this rule is set. But that rule is a hindrance. That rule is like a problem here in this type of scenario. So in this type of scenario, to overcome that, you need to have full mesh, which is this one. Means if I have 100 routers, I will have 99 neighbors on each router. Definitely it's a drawback. It looks like a drawback because you have to form 99 BGP session, 99 keep alives every 60 seconds. 99 times an update needs to be duplicated and sent to 99 different people. Definitely it sounds that not a scalable one. But the good news is we have MPLS, VPN. When you can put a VPN between B and E, then there is no need even for BGP to run on D and C. There is no need for D and C to run BGP. There is no need for BGP to run on D and C. When you can put tunnel between B and E. See, that is MPLS solution. Let us not focus on MPLS now. Is there any other solution in BGP? Yes. We have solution in BGP. Without MPLS also you can solve this full mesh problem. But no one uses it in today's world because we have MPLS layer 3 VPN. Now, what is the BGP's own solution for this problem? To avoid full mesh, you can create small sub-autonomous systems inside this autonomous system, so that you will have lots of eBGP inside the autonomous system. See, this rule is route learned via an IBGP or never propagate to other IBGP. What if I make two sub-autonomous systems here? The main autonomous system is this 65102. Inside I create some sub-autonomous systems. Like, just for example, I'm writing 65531 65532. Now, according to D and E, they are eBGP. There is no problem now giving. Whatever D learns from B, it will now give it to E because E is appearing like another autonomous system. Likewise, whatever E has given to C, C will give it to B because B and C appears as if they are in two different autonomous systems. Yes, they are two different sub-autonomous systems, right? So we call this concept as confederation, creating sub-autonomous systems to create eBGP relationship inside an autonomous system. Again, it's a costly solution, and no one wants to do this because we have MPLS layer 3 VPN. There is also one more, along with confederation, we'll be using route reflector. Route reflector is even used now, along with the MPLS solution. Route reflector, meaning by default, because of this BGPs, this is what called as BGP split horizon rule. Because of IBGP split horizon rule, route learned from IBGP is not given to another IBGP. To override that, we can say no, it's okay. You can go. You can tell D it is okay. Give it. Reflect it. After all, E is your client. You can say E is your client. You can reflect it. In that way, also you can override. All right. So we learned in this chapter that there are two behavior, two different characteristics, two different ways that BGP works. So two different names. One is eBGP, the other one is IBGP. It's not simply two different names, they also have two different characteristics. That's why two different names. Yeah. So the rule saying BGP need to be directly connected is a default behavior. You can still overcome it by doing some additional tunings, by setting some routes, which we are going to see in the practical chapter, which is next. Configuring BGP is the next chapter. So there we'll be seeing how to override all these default behaviors. In this chapter, the most important thing that we learned here is whenever whenever we have BGP in the transit autonomous system, redistribution is not a good solution, though some people do it in the production and face a lot of trouble. It's not a good solution. And then we saw if you're running only BGP, not MPLS, then you need to make sure it is fully mesh because route learned from an IBGP will not be given to another IBGP to prevent loop. If you don't run BGP on the C and D, you have to put tunnel between B and E. If not, there will be a black hole. Packets will get dropped. Right? With this, we conclude this chapter. Any question?